Hello physics students. Today we're going to determine the capacitance of a cylindrical capacitor. And what I mean by that is a small cylinder inside of a larger cylinder. One example of a cylindrical capacitor is the coaxial cable that I mentioned earlier in this course. A long skinny wire inside of a shell of metal, and that shell is used to sort of shield the inner conductor when it's transmitting communications. So we're going to calculate the capacitance of such a capacitor, but I just want to remind you or ask you, do you remember the 4 steps of deriving capacitance for particular geometry? Because this is the third and final geometry that we're going to study with capacitance. So at this point, you should know that procedure that we applied to the other 2 geometries. Now, obviously, they're written behind me, but if you close your eyes, pause the video, and think about it, can you think of those 4 steps? If you cannot, then I suggest after this video's through, you stop the video and then you try and study those 4 steps so they're fresh in your mind and you're ready for the test and you could derive the capacitance of any of the studied geometries that we've done. So let's begin. We've got here a diagram of a cylindrical capacitor, and it's got 3 radii. Radius A is the radius of this inner conductor. Radius B is the radius of this inner surface of the outer conductor. And radius C is the outer radius of this outer conductor. And the length of this wire, this coaxial cylinder, must be much, much longer than C for our analysis to work. So infinite in terms of the relative parameters in the given problem. So what I do is I charge the inner conductor, positive or negative, it doesn't matter. Let's just say positive, just, to stay consistent with our derivations. And then how do I charge the outer one up? All I need to do is connect it to the earth. This is a symbol for ground, connecting to the earth. And what will happen is electrons will be drawn toward this positive inner conductor just the right amount so that it accumulates the same amount of charge as the inner conductor. Furthermore, that charge will settle on the inner surface, not evenly throughout because this is a metal, and so the electric field where my finger is must be 0. So that means that all the minus has to be on that inner surface to shield the positive from the metal. So, and then the rest of the metal's uncharged. So the other thing I want to point out is note that the electric field is 0 inside here because it's a metal, and we learned that about conductors. And it's also 0 for, oops, I made a mistake here. This should say R greater than B because, again, as I mentioned, it's 0 inside the conductor and beyond. All right, so the 4 steps. The first one, we use C equals Q over V, the definition of capacitance. The more charge something stores for a given voltage, the higher the capacitance, its ability to store charge inside of its metal. So then we realize that in order to evaluate this, we've got to determine what the voltage means. And in order to get voltage, you have to first get electric field. So that's the second step, the electric field. What I've done here is I've drawn a Gaussian surface. This Gaussian surface, hopefully it's clear, it's in this air gap or plastic or whatever is here. This is the cylinder. It's going through this region because that's the only place where the electric field is. And I use a different symbol L, lowercase l, because I already used capital L. So this is shorter than the length of the conductor because I'm staying in the middle so that I could think of the conductor as infinite in length. All right, so continuing on, the flux is only through this outer surface, which again, remember, for cylindrical symmetry, when I open this up, I could think of it as a rectangle. And the area of this is the length, L, times this other length, which is the circumference of a circle. 2 pi r is this length, times L is the surface area through which this electric field pokes out of the flux. And then the Q enclosed. To calculate that, I need to determine lambda times L over epsilon 0. That's what I'm doing here. And the lambda will be the total charge over the total length. So there's lambda. The coulombs per meter times the meters gives me the coulombs inside my Gaussian surface. And then I solve for E, and there I am. Okay, so then the next thing that I'm going to do, now that I have the electric field, remember, I'm trying to get the voltage. So I calculate the voltage, and I do that through the definition of voltage, which is negative the integral of the electric field from one point to another along a path. Remember, voltage is the electric field along a path integrated. Okay, so here's my electric field expression times dr. I lumped all the constants together, the limits. So if I do a little cross section here, so here, like this, and like this. This is looking at the end of a cross section. I know that the electric field only exists in this region and it points outward because this is positive. So to get the voltage, I want a positive voltage to get a positive capacitance. So I'm going to start here and integrate to here. So this is my initial point, and my final is right there. In other words, from radius B to radius A. Okay, so there's the setup. Now, if you need a chance to catch up, let me create a pause for you to do that. Okay, moving on. Now we're going to evaluate this integral. Constants can move out, and dr over r integrates to natural log for the limits from B to A. I plug in my limits, log of A minus log of B. Now this minus sign will distribute through to make this log of B positive and this log of A minus. So when I combine the logs, when I subtract two logs, I can put the arguments of the logs together into one log with a subtraction as a fraction. Again, this was positive, so it ends on the top. This was negative, so it ends on the bottom. So there's my voltage between these two conductors. Now, to get the fourth step, to get the capacitance, I return to C equals Q over V. There, I took the charge, put it over the voltage, and notice the Q's cancel, and then this 1 over 2 pi epsilon 0 L flips up to the top, and I have this expression. By the way, I cannot bring the log up by calling it log of A over B. It doesn't work that way. It's got to stay in the bottom. So this is the capacitance of the entire conductor. So if a coaxial cable stretches from one end of the house to the other, we take the whole length of it and put it in the formula right there. And of course, epsilon 0 and the ratio of the two radii of the inner conductor and the inner surface of the outer, and we got the capacitance in farads. But sometimes in cylindrical conductors, because we're dealing with coaxial cables, we often cut a length of it for a given application. Maybe you want it to go from a TV to an old DVD player, or maybe you want to go from one end of the house to the other. So we got this cable, we're going to cut to different lengths. So often it's customary to solve for the capacitance per length, the farads per meter. And then when you know that, you could say, okay, I have this many meters of cable, it's this many farads per meter written right on the wire spool. All you have to do is multiply by the meters to get the farads of the coaxial cable. So that's the other, now the other possibility for capacitance of a cylindrical capacitor. So let me create a pause to allow you to catch up if you need it. Okay, now why do we care about the capacitance of a cylindrical capacitor, particularly with a coaxial cable? What can happen is when you're using a coaxial cable for communications and the electricity is vibrating, oscillating, some of the charge gets sort of stored in the cable itself rather than getting to the destination. Ideally, you would want to send charge out of the source and have it all go to the thing that you're sending it to, like a television, for example. But if the cable's too long, it has enough of a capacitance where a significant portion of that charge is actually just getting stuck in the cable and oscillating into the cable and out and not getting to the destination. And so you need to know the capacitance to figure out kind of the losses in that situation. So that's kind of one application of capacitance in a cylindrical capacitor. All right, so that's it for today, but I just want to remind you, 4 steps to calculating capacitance of either parallel plate, spherical, sphere within a sphere, or cylindrical, cylinder within a cylinder. Those 4 steps, can you name them? Okay? If you can't do it, study the 4 steps. Use C equals Q over V. That's where you start. Then knowing you need the voltage, you get the electric field using Gauss's law. Boom. And then once you get the electric field, you integrate that to get voltage, right here. Once you get that, you plug it back into C equals Q over V and simplify. That's how you figure out the capacitance of any geometric shape that we studied. All right, so that's it for today. I'll see you in the next physics video.